In this section, we are focusing on attacking Unix systems via CUPS, Common Unix Printing System. Specifically, we will be examining the vulnerabilities introduced by CUPS browsed. Understanding these vulnerabilities is essential for securing Unix environments. We will cover various CVEs that highlight different types of issues within CUPS, such as UDP binding problems, IPP attribute handling flaws, PPD file sanitization issues, and vulnerabilities that allow command execution via foomatic-rip. These will help us to identify threat vectors and explore potential remediation strategies to mitigate these risks effectively. In this section, we're going to focus on new attack techniques targeting Unix systems through CUPS, the Common Unix Printing System. Our goal is to understand these vulnerabilities, recognize potential threat vectors, and explore strategies for mitigation and remediation. We'll cover several specific vulnerabilities that have been identified. 1. CVE 2024-4776, which deals with UDP binding issues. 2. CVE 24-47076, focusing on IPP attribute handling flaws. 3. CVE 2024-175, addressing PPD file sanitization problems. 4. CVE 24-4177, involving command execution through foomatic-rip. Understanding these vulnerabilities will help us protect Unix systems from attacks that exploit these specific weaknesses in CUPS. The Common Unix Printing System, or CUPS, is a critical component in many Unix-like systems. Understanding the importance and relevance of CUPS is vital because vulnerabilities within this system can have severe consequences, particularly due to its widespread use. Exploits targeting CUPS can result in remote code execution, which is particularly dangerous as it allows attackers to control affected systems. Practical implications of such exploits include unauthorized printer installations and the execution of arbitrary commands. Recognizing why CUPS matters in securing Unix systems is the first step in appreciating the potential impacts of these vulnerabilities. These are not just theoretical risks. They can lead to significant security breaches in real-world environments. Understanding the vulnerabilities in CUPS, particularly CVE 2024-47176, is essential for maintaining secure systems. This specific vulnerability arises when CUPS browsed versions up to 2.0.1 bind to UDP on IATA ANI 631. What makes this issue significant is that it allows the service to accept packets from any source, which can result in unwanted IPP requests being directed to attacker-controlled URLs. The impact of this vulnerability is the potential for unauthorized remote instructions, which could severely compromise the security of your system. Our goal is to recognize and mitigate these risks to keep our printing services secure from exploitation. Let's take a closer look at how we can identify potential vulnerabilities related to CVE 2024-47176. This slide provides an example command sequence for detecting and investigating open UDP ports, specifically focusing on port 631. First, we can use the netstat command, netstat-anu grep 631. This command will help us detect any open UDP ports that are communicating through port 631, which is associated with CUPS, Common Unix Printing System. Next, to identify which process is using this port, we can utilize the lsoft command, lsoft-i 631. By running this command, you'll get a list of processes bound to port 631. When analyzing the output, be vigilant for any suspicious activity or unauthorized connections. This step is essential to identify any exploitation attempts that may leverage this specific CVE. CVE 2024-47076 highlights IPP attribute handling flaws in CUPS filters versions up to 2.1b1. These vulnerabilities stem from insufficient sanitization of Internet Printing Protocol (IPP) attributes. Attackers can exploit this by manipulating attributes to inject malicious inputs into the Common Unix Printing System (CUPS). This poses significant risks, such as the potential for injecting controlled data into the CUPS system, which can lead to unauthorized actions or the execution of harmful commands. It's imperative to address these flaws to secure printing services and prevent exploitation. Let's look at an example command related to CVE 2024-47076. The first line uses the epserver tool to send a malformed IPP attribute. Here, the attribute location is assigned a value of malicious value command to execute. The goal of this command is to demonstrate how an attacker could potentially manipulate the IPP attributes to introduce malicious inputs. Following this, we have a second command using curl. This command checks if the attributes have been properly sanitized by sending a GET request to the printer's IP and port, specifically to retrieve the printer attributes. This can help verify whether the exploit was successful in injecting controlled data into the CUPS system. CVE 2024-47175 relates to PPD file vulnerabilities in the libppd library versions up to 2.1b1. These versions fail to properly sanitize IPP attributes when writing to PPD files, which opens doors for data injection by attackers. This security lapse can lead to the execution of malicious commands. Essentially, it allows attackers to insert their own code into the vulnerable system through the unsanitized attributes, potentially compromising the entire system. It's a significant example of how important it is to ensure that all input data is properly sanitized before any processing or storage occurs. CVE 2024-47177 centers around the foomatic-rip filter within CUPS filters versions up to 2.0.1. This vulnerability allows for arbitrary command execution by exploiting the foomatic-rip command line parameter. The essence of the issue is that it enables attackers to gain control over the execution flow, potentially compromising the system. By leveraging this parameter, malicious actors can inject commands that the system will execute, leading to unauthorized control and further exploitation opportunities. In this slide, we explore a real-world scenario of an attack leveraging the CVE 2024-47177 vulnerability in foomatic-rip within CUPS filters. Let's go through the example step by step. 1. An attacker begins by sending a specially crafted UDP packet to port 631, which is associated with the target's print service. 2. The CUPS browsed service on the target system receives this packet and attempts to connect to the attacker-controlled IPP server. 3. This malicious IPP server responds with crafted attributes that include an exploit command embedded within the printer's attributes. 4. These crafted attributes are then written to the PostScript printer description (PPD) file on the target system. 5. When a print job is subsequently triggered, the exploit command embedded in the PPD file executes, allowing the attacker to achieve arbitrary command execution on the target system. This scenario illustrates how a seemingly benign interaction, such as connecting to a printer, can be exploited to execute arbitrary commands, highlighting the importance of securing print services and validating any external inputs. Now, let's take a look at an attack demonstration. Here we'll see how to craft a malicious IPP response using a script. The example provided uses the upserver library in Python to set up a dummy IPP server. In this code snippet, we've defined a malicious IP handler class that inherits from IPP request handler. The method respondGetPrinterAttributes within this class pretends to provide legitimate printer attributes. However, among these attributes, we include a malicious command. In our case, the command is touch tmp-hacked-n, which is meant to create a file named hacked in the /tmp directory on the victim's machine. To put this into action, we instantiate an IPP server on port 631 and pass our malicious IP handler to handle any requests. By running this script, the server will continuously respond with the crafted malicious attributes. When the print job is processed by the target machine configured with CUPS browsed, the embedded exploit command gets executed. This scenario effectively simulates how an attacker might compromise a system by exploiting printer service vulnerabilities. On this slide, we focus on the initial steps to mitigate the risk posed by the demonstrated attack. The first measure is to disable and remove the CUPS browsed service, which is a critical step in eliminating the attack vector. To disable the service, you need to execute the following commands: bash sudo systemctl stop CUPS browsed, sudo systemctl disable CUPS browsed. These commands will stop the service from running and prevent it from starting again automatically. Next, to completely remove the package, use bash sudo apt-get remove CUPS browsed. By executing these commands, you effectively remove the vulnerable entry point that the malicious IPP response exploited. This approach ensures that the CUPS browsed service, which facilitated the execution of the crafted response, is no longer present on your machine. This step is essential for hardening your system against similar attacks. Now let's move on to the next step in securing your CUPS setup, updating the CUPS package to its latest version. Ensuring your software is up to date is a fundamental security practice, as updates often contain patches for known vulnerabilities and improvements in functionality. To update the CUPS package, begin by refreshing your package lists with sudo apt-get update. This command will make sure you have the most current list of available packages and their versions. Next, execute sudo apt-get install only upgrade CUPS to install the latest version of CUPS without changing the status of other packages. This step ensures that your CUPS software includes the latest security patches and features, reducing the risk of exploitation from known vulnerabilities. By maintaining your software up to date, you create a more robust security posture for your system. In this section, we're focusing on network protections to enhance the security of your CUPS setup. First, let's talk about firewalls. It's important to block all traffic to UDP port 631, which CUPS uses for some of its network functions. You can achieve this by running the command sudo ufw deny 631/UDP. Next, we need to ensure that the CUPS services remain isolated from the broader internet. This isolation helps to mitigate the risk of exposing your printing services to potential external threats. By implementing these firewall rules and isolation practices, you can significantly reduce the attack surface and protect your CUPS installation. In conclusion, we have identified the critical vulnerabilities in CUPS systems, demonstrated exploitation techniques, and discussed the potential impacts. Importantly, we've provided actionable mitigation steps. As next steps, it's vital to regularly update your system packages and implement robust network security best practices. Additionally, consider disabling unnecessary services to further minimize risks. This holistic approach ensures a secured and efficient CUPS environment. On this slide, we have a list of references that will be beneficial for further reading and understanding. The first reference is EvilSocket's blog post, which offers an in-depth look into specific vulnerabilities and exploitation techniques. Next, we have the Ubuntu CUPS docs, a useful resource for detailed configuration and setup guidelines. Lastly, the Linux Manual on CUPS Browsed provides comprehensive documentation on this specific daemon, which is crucial for networked printing setups. These resources together will help you deepen your knowledge and effectively secure your CUPS systems.